Right. So I'll call this one E1, and I'll call this one E2. Now what I'll do is to try and get the union of this thing. Now we do understand that the union is just everything that is defined within E1 and E2. So if I just color it up to you. So here is our union. And a while ago we said that it's letter U, standing for union. But what we'll do now is to count things inside of it. And normally in mathematics, how do we know how many elements is inside of E1? If I want to be in particular, if I say that E1 is A, B, C, how do I count the number? Like normally if I ask a human, we would just say 3, right? There's 3 elements. But how do you write it down in mathematical terms? So yeah, very good. It's an N. So if I put N, put E1 inside of it, it tells me that's 3. Do you know where this kind of writing label came from? What does a parenthesis stand for? It's a function. Right? So this parenthesis stands for a function. As humans, we already understand what this one would do, right? But what we're doing is, N is a function that would count the elements. So if I put E1 inside of it, it would process E1 and find how many elements it has. So this is actually a function, but we're not aware of it too well. It is a function that counts. So if I put E2 there, how many E2 would be? It would bring it up. I know this is like, what do we need to talk about? There's no nonsense. But anyway, it is how things are there. I just want to show to you that parenthesis is a function. But somebody might be very philosophical. How do you prove it's a function? I need to do the vertical line test to prove it. It's somehow very hard to prove, right? Because this thing is a counter. It counts things, but for us it is related to a function. But anyway, I just wanted to show you that. I'll just put it here so it's easy to grab. So let's have another one, which is E2. What do you want? Well, there's an intersection, so maybe I'll just... Alright, so then I have an N E2 there, which is 4, right? Now I'll ask you is what is that? 1. Of course, there's only one of them, which is the intersection. So how it's asking you, what is the intersection? So first I need to solve it. Answer is C. And if I put this inside my function, it only sees 1 and ends up here. And the next question is, what is this? Seven? Is it 6? It's 6. Right, and why is it 6? Because we don't write things double, right? We combine it, A, B, C, but we don't write C again, because C is already present in those. D, E, F. So when you put this inside of that, it counts 6. But our problem is, how do we make an equation that can just do this all at once? Because it's easy to do this because we can see the elements. How about if we don't see the elements? Well, there's a way to do it, right? There's a formula, and I do understand that you know it. Here's the formula. The intersection of two events, the union of two events, is equal to the number of event 1 plus the number of event 2 minus, right? The intersection. Right. Does it make sense? Let's try it out. So we have 3 it does work out. So it's all happy and dandy. But how did we prove this? Is it something that we just got from the book, or is it something that we can actually show to them? We can show it to them. So let's try to show it to them. And the only way I can show this to you is to use 3 colors again. So let's try. Alright, so I know that the union is having all of this together, combining it. So let's try that. Here's E1. And here's E2. Yeah. Okay, so now what we do is we add it together. I'll try and add it, right? So if this is only interactive, I can just like move this around, but it doesn't. Alright, I'm actually creating that in my house right now using a 3-dimensional projector. So I can hold it and I can drag it. It's not finished yet, but I'll make a YouTube video showing to you that I'm constructing it. Anyway, here we go. I never told you what I am really. I am a physicist. So yeah. So I do create things, and in particular, anything that's high in energy I can create. So lasers can also be one of my forte. So I compute angles of lasers, trying to make them interact with computers so you can drag things around. Alright, so here we go. Let's look at this. We have like a red part and a black part. So if I try and get, the only thing I need is a shape that looks like an 8. Like I only need that shape, right? I only need that shape. So what it tells me is, I'm only concerned about that circle, so let's try it out. So we have that. And you notice that if I only get that, there would be a part that I don't get, right? Like I don't get this. I'm like removing it from my equation. But what's this? What is that thing that I remove?
The intersection.
Right, it's the intersections, and that's. All right. And now I have the other color, and I know you would react to this. I'll try to remove this again. And you see that this is also E1 intersection E2, right? And if I try and combine these 2 coconuts together, it looks like a coconut. What do I get? Well, I get the shape that I like. But the problem is, I think you need to be aware of what you're drawing, because sometimes it looks something. So anyway, I just want to tell you that be aware of what you're drawing. Sometimes we are so deep into what we're doing, we don't look at what does it look like from afar. So are we close to what we want? No, right? There's a hole. There's a hole. We don't like that hole. We need to fill that hole in. So right now, what I'm trying to do is, what does this represent? This represents the number of outputs. I need to be very consistent with what I use, large N. It's E1, and I removed this, so how would I represent it? So this red coconut is that. Removed that small part, like beaten off by Cookie Monster. And this thing is the number of E2 beaten off that thing. right? Now what I did here is I combined them together. So I just added that and that. You know what? I'll just use the red one for that, so it's easy for us to understand that it came from that one. And you know, by doing this, you can teach your students that adding things in the Venn diagram is the same thing as adding normal numbers. So it's no problem for us to add things that looks like this. Alright, so now let's add that. And the result would be, let's put it here. I just want to put things that looks alike on the same side. Right? Now there's two of this. So normal mathematics tell us to put a coefficient. Oh, here we go. But it's a minus. So there's two of that, two minuses. I'm just adding everything. Alright, but is this what I want? Not yet. As you can see, there's a hole in there. If I want to fill that hole in, what do I do? What do I add? Right, I need to add, and this is where I can use your the green one. So if I add that would be perfect, right? Everything I want. So let's see, let's draw that now. So I added this to my previous color red. And now it's perfect, right? It's all the things I need. And adding that to my equation, I need to add this. Oops. And once I add that, what do I get? Which is exactly what it is on top, right? So, right. So it's perfect because it's exactly the equation that we have on top. So that's a visual way of proving it. There's many other ways of proving it if you want. There's like a matrix algebra way of proving it, but we will go into that maybe in the second week. I want you to understand how to use a matrix algebra to prove all of these things that we have in probability. Alright, but that's the easy way. This is how we just show it to our students. Do you show this to your students? Or maybe they're like, what's the purpose of this in my life? Anyway, but as us teachers, it's better for us to really understand the underlying why it is like that and everything. But with having this equation, this is a really powerful equation you can use because it only means that if I give you a problem that involves a Venn diagram, we're giving you just this, that, and that, you can solve for that if you want. And reducing that is so powerful that you can solve all the Venn diagram by itself. Alright, I want to give an example problem which we would try to solve, all of us solve it, not individually, so just up to so it's not going to be a hard problem. But we're going to use this equation and see how powerful this equation is. Is this probability? No, it's not, right? It's not probability, it's just a number. Right? But we're going to use this to solve probability. And we will see that it's quite easy for us to solve probability by using this. Alright. out what is in there. Now, what is this 8? Right, it's the complement of the union. This 8 is a complement of the union. I want to show that to you later on. 8 students study neither language. It means that they don't belong here, they don't belong there, they don't belong here. They belong on the outside, but still on the inside of the box. So it means that there's only 8 students on the outside. If there is 30 of them only, then it means that for this to be 30, then the one which is inside of this coconut thing that I showed you a while ago is 22. And that coconut corresponds to that, right? 22. Which is the, oh, I'm sorry, the union. The union. So 22 corresponds to this union. Right, so now I can use the formula. I know that there is like, it depends on you which one you want to call E1, but always I want, whatever is the first one is my E1. So French is my E1, and there's 10 of them, and my E2 is my Japanese, and there's 16 of them. And now I can solve for the intersection, which is, this is what I want to find out. Understand it that X is N E1 intersection E2, that's what we want to solve. And by doing that, we have, what's that, 26 minus 22x. I just transpose it on both sides. And I want to have a really nice looking x, so I do that. And that would give me 4. And now I know what the intersection is. I can fully draw this thing. So this is 4. And I have 10, that is French, so for that to become 10, this should be 6. 6 plus 4 is 10. And that should be 12, right? So yeah, it's an inverted question, right? So if you do this first, I don't think you can. Some can actually, but you need to do this first before you can do that. Alright, our next step is to find the probability. Entirely correct. Let's change that into something that we do understand. It's equal to EI. Choose a particular event, right? EI. If it's E1 or E2 or E3, it depends on you. Over, and you need to know how many, right? You need to know how many of that events or the sets inside of the event is, and then divide it by the number of the universe or the universal set. So that's how probability is defined. And we can use this to find out the probabilities of all of this. So let's try to do that, and this is where things get a bit confusing, and I tell you it is for some people. Right? So I'll write it down. First question. What is the probability of E1? And what it means is, what's the probability of you studying French? Right? This thing means, in English, probability of studying French. Right? So it's an easy thing. We need to get the number of elements of that particular event, which is E1. In that case, it's French. And we know there's 10 of them. It's 10 that studies French. So that's as easy as the number of E1 over the number of the universal set. And we have 10 over 30. So we have 1 over 3. So that's equal to 33.3%. Now, when you teach your students, somebody always asks this: how many decimal points would I write? You always ask that to you, right? So what do you tell them? What do you tell them? Like, how many decimal points? Like 1, is it enough? Is it 2? 1 is 10. And the number of the intersection is 4. And this is 30. So that's very clear. It shows us everything, and then students would ask, how do I write that? Well, just fraction. Let's go with fraction, 1 over 5. So that's good enough, right? So this is showing to them how it all works in terms of our definition, because that's what we need to do. Alright, so the same thing would work out for Japanese only. I don't need to write down. It's also the same thing. In terms of this, it would look like probability of E2, right, minus the intersection. And then just go on with all of this, it will just be the same. But what's important is we can convert it into mathematical symbols. Alright. Now here's the next thing. Probability of taking at least one language. Now that's always a problem, right? Is that? Yeah. What's the probability of getting at least one language? Now somebody said 22 over 30, that's correct. What's that, 11 over 15? Yes. Right. Did everybody understand why it's 22 over 30? At least one means either you study French, or you study Japanese, or you study both, right, but not studying neither. So it means that only 8 did not study anything. And you should at least study 1. And this 8 did not study everything. So here goes the definition of how we define the thing that's not included in it, and how we try and get a formula so that we can just easily get the probability of the other one. So let me just show it to you. Studying at least 1 is the complement of not studying, right? It's true. So let me show it to you.